Okay, hi all, welcome to this scientific seminar. We have a great pleasure to host today Dr. Valentin Walther from Purdue University. Let me say a few words about Valentin's academic steps. So Valentin did his bachelor in Frankfurt at Goethe University. Then he moved to Stockholm for a Master of Science. Then he did his PhD at the Max Planck Institute for Physics of Complex Systems at Technical University of Dresden, and then he received the postdoctoral fellowship from the Institute of Atomic Molecular and Optical Physics at Harvard, where I had the pleasure to share an office with him for 1.5 years, if I remember well, right? Yeah, okay. And then he moved to Purdue, where he is now an assistant professor. His group and his main business lie on the energy of Rydberg stations. Today he will talk about exploring Rydberg polaritons at the boundary of weak and strong coupling. Looking forward, the stage is yours. Thank you.
Technology work. Yes. All right. Fantastic. Okay, so thanks for the introduction. Thanks for having me. It's already been a very exciting day. I've had super exciting discussions with faculty, but also with the grad students. So that was really nice. And I hope that we can continue those during and after the talk. And I can talk about Rydberg states. And like one of the fascinating things properties of Rydberg states is that they somehow take us back to the origins of quantum mechanics. So what we see here is the longer series of hydrogens, so basically the emission of light that occurs when an electron from a highly excited state of hydrogen falls back to the second excited state, the n equals 2 state. What should I do to it? Just do it. It is? Oh, yeah. Okay. So that's the longer series. Rydberg states spark the observation, or like the usher in the development of quantum mechanics. And I think that's because they're so universal. So you find Rydberg states and their universal behavior in all sorts of atoms and in all sorts of other systems as well, as I will show you in this talk. And so as we speak, like Rydberg states are again rising to the forefront of our attention in quantum information science, but partially because of the same properties, because of the universality that you find across all sorts of installations of Rydberg physics that are very controllable and therefore can be exploited for applications. Okay, so just a primer on Rydberg. So these are just the very first states of hydrogen species, and so on, like the first couple of states, and like a name that will, or term that will turn up many times is the principal quantum number n. So you see that as we change n of the principal quantum number, the state already becomes very large. So that's immediately clear. Here's the scale, but it's not only the size of the state changes as n is changed. So here is the square of the principal quantum number, but at the same time the line width goes down, but the cube of the principal quantum number, or in other words, the lifetime goes up. The binding energies get smaller as you approach the ionization continuum. And very importantly, the interactions between two Rydberg states scale as the 11th power, roughly, and universally with the exponential quantum. So that's a tool that allows us to really switch on, toggle on and off interactions between atoms, for example. Okay. And so this chart illustrates this. So here you see kinetic particle interactions, van der Waals interactions in the ground state. But for all sorts of particle interactions, particle separations in the micron range, van der Waals interactions of here archetypical Rydberg state 100 F S are dominant. They dominate by far over all sorts of other energy scales. And what this allows us to do is to implement an effect called Rydberg blockade, which essentially means that if you have two Rydberg atoms, say, and you try to excite them to the Rydberg state, then this will proceed by an intermediate step where either the first atom is excited to the Rydberg state, the second is in the ground state, or the second is in the Rydberg state, and the first is in the ground state. And from there, you would think that you can excite to a doubly excited state with two Rydberg excitations, but then you have to pay an energy penalty that comes from the Rydberg interactions. If that interaction is very large, then a situation can arise, that's shown on the right, where you just can't go to this Rydberg state. And so then you're left with a situation as here that can, as we actually just discussed with the graduate students, be used to entangle atoms. Okay, and so these strong interactions and in general exactly properties they have been used or are being used in all sorts of technology and science applications. So I just show you some of my favorites. So here that shows like how you can use you can use Rydberg states to detect microwaves, like outputting like isolating states that then split under the effect of a very weak microwave field. You can use Rydberg states in quantum simulation. So they are some of the most controllable systems around. Here, the group of quantum from the Institute of Teaching has managed to build an SSH model in a lab. And so you can really see, like, basically under a microscope, you can see the topological, non-trivial ground state of this model. You can now that's really like rising to the forefront of the media. You can use Rydberg states digital quantum computers. So the idea is that you store qubits in two hyperfine states, hyperfine ground states of rubidium, for example, and then you can move them around to optical tweezers and basically implement arbitrary gates between them. And I think the record today is 49 logically characterized, or logical, that is characterized qubits that can be implemented. And then, last but not least, like this is probably closest to my own heart, you can use Rydberg states to create very strong optical nonlinearities down to the level of single photons. So that's an experiment here from Gerhard's group at MPQ in Munich that implemented photonic CMOS gates using Rydberg atoms. Okay, so today I will tell you two stories that kind of guide my research and that are connected by this overarching theme of Rydberg excitations. And in the first, I will really talk about like Rydberg excitons, that's solid state excitations, and how we can turn those into polaritons to help them apply. And in the second, I will return more to an atomic themed research direction that talks about, giant dimers of rubidium. Okay, so let's start with the first topic. And I know that many of you do, in all physics. So let me just show you that this basic picture. So if you have a semiconductor, you can excite electrons, and this actually flipped, I don't know, I corrected this morning. So you can excite electrons from the valence to the conduction band by sending light into that semiconductor. So initially, the valence band is completely full, the conduction band is completely empty. But if you have laser light that can bridge this gap, you can free up electrons, they will float around the semiconductor, and that's the process that, for example, leads to electric conductance. So, but in some situations, if you illuminate with a laser that just doesn't have enough energy to completely free up the electron, you can still excite particles in the system. And those particles are pairs of electrons. So basically the electron doesn't have quite enough energy to completely leave all that it creates, but still bound to it. And so I want you, for the purposes of this talk, at least to think about these excitons as basically atoms in the solid state. So they're bound in the relative coordinate. But together, the electron and the photon move freely throughout the system. Okay. So this field of exciton physics has been known for many decades. I think it goes back to Russian research at St. Petersburg. And that's a typical, absorption image that you can take of such an exciton. So you see one resonance here, that's the exciton. When you hit it, you create excitons. If you go a little higher in energy, you basically get the hit the absorption continuum of creating three electrons. And typically, you just see one of these excitons. And that was the situation until a couple of years ago, when this material came around, this copper oxide, and it didn't really come around. Like copper oxide has been actually like one of the first materials for excitons everywhere. It's covered, but it was remeasured from an anniversary, like the exciton series was remeasured. That's like the paper that or like the picture that I took from this nature paper. That's another picture, like where you see like how beautiful it can be when you polish it down. And it turns out that this material actually has an enormous series of Rydberg states. But it doesn't only like there's one peak, it has many peaks. So here we see like this first exciton resonance, and then the second one, the third one, and the fourth one. And then if you zoom into this last image of the spectrum, and then you see that there are more peaks, and then you zoom into this last peak, and then there are more peaks, and then you zoom into this. And there's an entire beautiful series of Rydberg states in that material. So that was kind of the situation, and like knowing, my background is in atomic Rydberg physics, and so what I really wondered about is like, what can you do with these semiconductor types of Rydbergs? Can they also be used to give us strong interactions to our kind of the feel of all of the interesting models and stuff that we're interested in? So basically, the question is like, is there a route to strong interactions using these things? And so to answer that question, what we have like some sort of handle of what the interactions actually are between excitons. And so if you look at the textbooks, you'll find that excitons interact via collisional interactions, and the basic principle is that when two excitons bump into each other, then they discover that they're really fermions, two fermions or four fermions under the hood. So there's Pauli exclusion, and you really get like a repulsive interaction that becomes effective when the wave functions overlap. But because the size of an exciton is roughly a nanometer, the length scale of that interaction is roughly a nanometer. Now, we know that Rydberg states are pretty different, but as I told you before, they're more polarizable. And so, if there's a polarizable model, we expect that the polarization that's not a long range and probably in the high micro. Whether it's very mechanical way, I think that you make that like much more complete. So let's take two Rydberg states and let's just calculate the interactions out of the issue. So, at a very large distances, and we're focusing here around the n equals 15 and n equals 15 resonance, you have just see basic product states of one atom being one state, and the other atom being and the other state. So 15 p 15, and then going to give other states here. But as you go in, you see that actually like these lines that are like curving upwards, and that's like this typical where you get like this distance dependence of some constant divided by halves. And if you go even further, then all the mixing, scrambling, and the atomic physics that's known as spaghetti region. Okay, so we don't want to worry about the spaghetti region right now. Instead, like you can actually use certain symmetries of the system, and in this case, that's the projection of the total angular momentum of the two atoms onto the axis that connects them. That's a conserved quantity. That's how to be a conserved quantity. Doesn't matter now, like the details here. What I want to say is that you can use that to distinguish all of these lines and to extract the coefficients, basically the C6, that you divide them by r to the 6, you can extract that. And you can extract that for n equals 15 and for all the other principal quantum numbers. And so that's what I did. And so here you see like this extracted, numerically extracted C6 coefficient, and you see it's roughly constant on that scale. But you'll note that I divided it by energy level. So here we recover that the interactions, the van der Waals interactions, the Rydberg, so to say, interactions between excitons to the nth scale as some constant to the 11th power. And now you might say, well, that's not all that surprising, like seeing that we in general expect that type of scaling for Rydberg states. But what perhaps is interesting to note is that if you compare atoms and excitons for a given principal quantum, so let's pick N15 because we looked at that example, then the interactions between the excitons is actually much stronger. It's almost 500,000 times stronger in copper oxide than the material that I showed you than between atoms. That's because of the reduced mass of the hole versus the nucleus and the dielectric screening in the material. So you have really strong interactions at n equals 50 that correspond roughly to n equals 50 and atoms. And so that's, the useful range for one number that is used in atoms, and now that we hopefully can also use in atomic systems. Okay, so now part of my trajectory has been, using these interactions that we calculated and then connecting them to experimentally measurable things. So, for example, the first thing that we tried was reproducing the measured nonlinearity. So basically, you have a laser, you let it propagate through a piece of crystal, and you measure transmission, and you measure how transmission changes as you vary the intensity of that incoming light. And so it turns out we can actually reproduce, or we can explain the measurement almost perfectly, quantitatively, using this Rydberg, these Rydberg interactions that Rydberg used. Then we can even go further into the details and using some pump probe scheme where you first pump a bunch, or create a bunch of electrons to one principal quantum number, and then you probe transmission at a different resonance energy. You get very specific signatures that are kind of like fingerprints of the interaction, and we can prove that the interaction between excitons really is this C6 or R26 type of behavior, rather than the contact interactions that we know for ground state excitons. Okay, so that's that, and that puts us on this, opportunities for quantum information charges. This classical nonlinear box. So that's basically when we're looking at larger photons and interaction strengths that are really low per photon. So it's not linear, but it's non-linear, but still, there are no correlations between the photons. They're still all classical in some sense. It's a coherent state. Now it turns out that the real promise, quantum, many design here analyze in a range where the attraction strength per photon is large. And you can think about very interesting applications like split switches, generation of non-plastic light, and photon transistors. So part of the goal is to go from here to there, and that's not enough. And let me just tell you that the state of the art in excitons, kind of producing some sort of quantum mechanical entanglement between photons is pretty poor. So one measure of that, I call quantum mechanical lightness, is G2. So the probability of an incidence measurement that you have two clicks at the same time, and the criterion there is that this G2 of the pure state needs G2 at 0 time, it needs to be smaller than 1. Then it's quantum. And so that's the measurement people did here, not on Rydberg states, but on ground states. So the paradigmatic examples on our side, I believe, two beautiful experiments, one in Natasha Hooper's group, one in Thomas Holz's group. And you see that here, that's the classical limit, and that's the tiny deviation that we see from the classical limit at 0 time. So that's to say that we get maybe maximally 5% deviation from the classical limit using just ground states. So if we can do any better than that, that's a success. Okay, so let me show you some ways of how you can probably do that. So the first is collaborative work with really Hamid Abdel's group here, and that talks about Rydberg exciton polaritons. So the idea is quite simple. So when you want to create entanglement in light, you better couple some matter degree of freedom to that light field. And the way you do it in semiconductor physics is you basically take two layers. Here there are fractioners, distributed fractioners, and you place semiconductor material in between, such that the photon that bounces back and forth between these pairs has many chances to interact with the single layer. Now, the thing about copper oxide is that it actually couples weakly to a light field. That's part of the reason why we see such a beautiful Rydberg series. And it's all the more impressive, I think, that the group of Hamid managed to still couple Rydberg states strongly to the line. That's what we see here. So that's a Cantor spectrum. The bright lights that you see are different longitudinal modes. So you can you see the photons light up, And then there are these basically horizontal lines. That's the Rydberg. Those are the Rydberg states that are dark. And they're flat because of the scale of in-plane wave vectors that we're considering here. They're just like basically, it's just so you see the n equals 3, 4, 5, 6 Rydberg state. And we can now see that whenever a Rydberg state crosses this photonic dispersion, there's an anti-cross. Like here, this line goes up, this one goes down, and that's the signature of strong power. So we can zoom into that, and here we see n equals 3, right? Like you see like two peaks, maybe not, but for n equals 3, we really see it for 4, 5, and 6. You see it as well, but like then for higher quantum numbers again, you don't see it. And we calculated this, so the experiment n equals 2, like lies under the strong power in the limit here. But for 2, the experiment really is in the strong power in the limit, and for all of the other quantum numbers as well, beyond that, it's not. So we do see strong power, maybe, okay, so that's a detail here. You see that these lines are slightly asymmetric. Other than atomic systems, there are more degrees of freedom. So you have the polaritons, you have a photon background, you have Rydberg state, and there's parallel excitation pathways, and there's coupling between the Rydberg state and the polaritons, and you can calculate all that pressure out. And it gives you this like hollow shape that's a bit asymmetric. And if you then integrate it into the cavity, then you get the solid lines here. That's the theory. So we actually can quite well reproduce what's seen including this symmetry. So we see from coupling, but what we don't see yet are photon correlations. And so there are good reasons for that. The cavities that are being used today are just too large, so the electrons don't get to see each other. But we're on the way. So that's like one step into that direction. Okay, so another direction, another experiment that I did the theory for basically is similar. It also talks about excitons in cavities, but not instead we're now looking at a different material. It's called the transition metal argonite. It's one-dimensional, two-dimensional. It doesn't matter. It's this material. I come back to it in just a bit. But what you need to understand now is that we just measure like an incoming beam or reflected beam, and then basically angle resolve reflectance spectrum. Okay, and these TMDs, they also have Rydberg states. They're not, you can't see them up to n equals 30. Now you can also only see them up to n equals 5. If you put on a strong magnetic field, see them up to n equals 11 or so. That's kind of cheating. So they're like overall, they're not really as pristine as the carbon oxide, but they're there. Okay, so what happens? So we again have a similar picture. You have the polariton, lower polariton, upper polariton. There's a gap between them. And now we actually change the intensity. So it's qualitatively different than the first experiment in that we now actually try to probe nonlinearities. And so as you increase the bump intensity, what you see is that this gap here gets smaller, smaller and smaller. And at the highest bump intensities, this gap is completely gone. And that's an interesting result. And it's an interesting result. So here I summarize it again, right? That's the energy. You have the two polariton peaks, and as you increase up intensity, like just schematically, the two peaks merge. And that is interesting in that it completely contradicts traditional theory. So traditional theory would say, well, you have, a sort of perturbative attraction that just depends on how much of the polariton is an exciton. And if you put that in, you would predict that both the lower and the upper polariton would shift the same pattern upwards. And so it's actually interesting to see that this perturbative treatment of the polariton-polariton interaction is incorrect. But if we really include this bouquet type of interaction, that if you have one exciton, then you cannot have another exciton in this vicinity, then you really reproduce this type of qualitative behavior. And we compare it with experiments where the group of Vinod Melon at the City College in New York, they tried this for two different quantum numbers, and we can kind of get a good agreement between theory and the experiment. And so I think that it really shows that you need some sort of experiments, especially if there are strong interactions, you need virtual bouquet theory to capture. Okay. So these are strategies, like to get towards the photon-photon entanglement regime that rely on really strongly coupling photons to matter and then having strong matter-matter interactions. So here, and so I will now show you two different alternatives to that approach, which don't rely on strong matter coupling, but you can still get photon-photon correlations. And so that's a collaboration with Thomas Johnson from the Niels Bohr Institute in Copenhagen. So that's completely theory now, technical experiment. So that's our semiconductor, and let's consider a situation where I don't have strong coupling. So if I want to measure some sort of photon correlation, then I basically have to look at photon correlations in transmission. So let me have a model that describes this image, because I have this box. So now let's send a Gaussian beam of light through that semiconductor, and wherever that Gaussian beam is, it can be side excitons. Now, that's resonant with an excitonic transition. So there's an exciton, and the dashed line around it denotes a blockade radius. So in the magnetic radius, we cannot have another exciton. Okay, but if the exciton decays now, right, it's excited by light, and if it decays, it can basically, in a stimulated emission process, it can decay it again into the same mode that it came from. But it can also decay into some completely different mode. So that would be loss, basically. And it turns out that for copper oxide, that parameter, like the ratio between loss into some other mode and loss, or like radiation into an organic case from is unknown. But for sure, like one could expect that loss to other modes is more prevalent than radiation into the same, just because the exciton isn't really strongly coupled. Okay, so now to investigate that, let's look at like how G2 looks like. So G2 is again like this bigger American that needs to be smaller than 1, and it's a time way to show that there's some sort of quantum correlation with light. So now let's propagate the coherent beam, for which laser beam, for which G2 is 1 throughout. Let's propagate that through the crystal. And let's see what happens. So on the left, I show conditions of high loss, low loss, and on the right, high loss. So as we go through this crystal, there's some structure formed. So G2 actually dips, so signifying the onset of quantum light, then becomes deeper and deeper. And here it really almost hits 0, and then it has some interesting structure, which is slightly different for high loss and low loss. So on the low loss, you have 5 correlations. So y in terms of the time delay, then you have perfect anti-bunching at some distance throughout the crystal. And if you go even further, then you get 0 time bunching. So the photons like to come out in pairs at the same time. If you have high loss, however, you have narrow correlations. You have still strong anti-bunching, but it's not perfect. And if you go even further than that, now the photons like to come out in pairs, not at the same time, but at a certain time difference. Okay, so that's a certain type of observation. Now let's try to understand that. So this is just the hand-drawn sketch of what happens in this material. So here you have absorption. We have monochromatic light that goes through the crystal. So it has one definite wave vector, that's K naught. And that wave vector is resonant, or the corresponding energy is resonant with a excitonic transition. So that would be this line that's supposed to be Lorentzian, somewhere close to that. So let's imagine you have like 2 photons coming through, and now they can scatter, right? They can scatter off each other because there's this interaction between the excitons they are coupled. And when they scatter, they actually get scattered into other momentum modes that are distributed around that K, and the distribution is roughly given by 1 over the blockade radius. So it's given by that immense scale. And so after that scattering process, it turns out this photon pair will propagate throughout the crystal, will continue to propagate through the crystal. But now it's spread, and so you can see that the momentum modes that remain resonant with the exciton have more absorption, or experience more absorption than those that have been scattered out of resonance and now propagate more freely or with less impedance to the crystal. So, relatively speaking, the modes that have been scattered become enhanced. So here, that's what we see here. So they have blue shifted photons and then red shifted photons. So in other words, that you have photons that travel through the crystal, now there's a scatter, and it's those pairs, entangled pairs of red and blue photons, or entangled photons that have a higher likelihood of making it through the crystal than those that haven't scattered, or stay at the resonance frequency of the exciton, and then couple the excitons that get lost into other modes. And so can we see quantum light? And indeed we can. So here, as a function of low loss, high loss, you see there are always regions where G2 of 0 is significantly below 1. So that would be this region or this region. And all you have to change, depending on that unknown loss parameter, so we don't really know, like 10 means here, like that loss into other modes than the incoming mode is 10 times faster than coupling to the mode, and here it would be 50 times faster. So even under those low, high loss conditions, I find areas here in terms of this, like 5 years in terms of the coherence length of the photon. So think like 1 and probably like a couple of tenths of microns. So you only have to couple the crystal at the right length, and then you will see quantum light come out. Okay, so that's those features are pretty stable. Okay, so now I should say that like if you look at a feature like G2 and transmission, it really that's a metric that enhances relation and high loss. The way they all the loss of light, they don't count. And so like the goal really is to deterministically produce entangled photons. And a slab of copper oxide, even if it's coupled to Rydberg states, won't do that. It will give you quantum light at a certain distance, but only very dimly. So you send in, well, it's a photon, so once in a while, an entangled pair of photons goes out. Okay, so there's another direction that we've explored and are currently exploring. I'll show you the first steps into that direction of how you can use the quantum mirror to produce entangled pairs of photons. That is in collaboration with Susanne from Harvard and Thomas Bolt on Belgium, I guess. Okay, so let's return to that material that I mentioned. Transition magnetite argonites, they look like this. They're two-dimensional. All I want you to know about these materials, I see some people recognize them, is that transition that these model layers are coupled very strongly to light, and so much so that if you send a single photon onto this two-dimensional layer, it will get reflected. And that is like some really amazing property that like thin atomic gases would never have. And so that's been seen experimentally. So here you see one flake of this material light up in transmission. So you see 85% reflection because the radiative process, the radiative coupling of this material is so strong compared against the non-radiative processes. If you shift that resonance somehow here by doping, then the resonance disappears, reflection disappears. So think of this thing as a mirror. And I just illustrate this here. So it's a mirror. So if you send in single photons, right, they will just bounce. Will bounce off that mirror. And now in AMO physics, there's the trick called electromagnetically induced transparency. Whoever doesn't do AMO physics, right, the technique is to laser couple the state, an intermediate state, the state that to have a second laser that basically promotes the final state into a long-lived state. So that could be a Rydberg state, and through the fascinating effects of quantum interference, you actually get transparency. So a sample that before was absorbing, so would absorb and scatter light, now it is no longer. And so in other words, single photons that would fly into this mirror would just be transmitted. And that's, it almost looks as if the mirror didn't do anything to the photons, but that's only partially true. In fact, you can calculate that every photon has a transmit fits to the mirror takes a picture of a time delay. And that time delay is given by the ratio between the lower radio frequency gamma and the upper radio frequency omega squared. So it's actually controllable, that's the time delay. So now if we want to think about photon correlations, we need to think about multiple photons. So let's take a bunch of photons and send them onto that mirror. And here, this final state is a Rydberg state, and that Rydberg state has strong attraction. So if I have one Rydberg state already in the ring, and then the second one has a different time also making it in. Okay, so now a bunch of photons coming in, and then one will go through the mirror, but in that time frame, it will partially populate this Rydberg state, and so the subsequent photons cannot also make this polariton go through the mirror. So the remaining photons will then be reflected from the mirror. And we can calculate that in transmission, and you see actually in transmission, you get a beautiful G2, goes all the way down to zero, and has a time delay just like the rise time here, when photons start becoming anti-bunch, we say, like when this happens on the time scale, just given by the time it takes a single photon to pass through the ring. So it makes perfect sense intuitively. If you crank up the intensity just a little bit, you get Rabi oscillations and interesting other effects on top of that. I'll not go into that too much detail right now. So I wanted to show you all of this. I had Rydberg excitons are good for making entangled photons, and now we're looking at in my group, we're looking at polariton scattering theory, we're looking at many-body dynamics of polaritons, how we describe those. We're looking at interactions with defects and at how you can maybe sense electronic states using these. Okay, so in the last 20 minutes or so, I will switch gears and leave the field of semiconductors and maybe take a bit more to the AMO audience here. And let's work at that now that we're walk and give you the real credit goes to the experimental graduate student and collaborator management on all of this. Really took like all the data that I'm going to show you. Okay, so let's take a step back first. So what do I want to talk about? So Rydberg states, I said, have like these long-range interactions. And that's similar, and I'm just sketching the picture that I showed you before, but now for two atoms. It's completely the same picture. You sometimes have repulsive potential energy surfaces, like the blue one, and you sometimes have attractive potential energy surfaces, like the red one. Now, it turns out, for the graduate students, like in quantum mechanics, potential energy surfaces don't in general cross, unless there's a symmetry that dictates that. So, in the absence of such a symmetry, like lines don't really look like this, but they look more like this. So there's a water crossing, and now you find yourself in a situation where the electronic state is the same along this line and along these lines. But you find really like there's like sort of potential well. And now if you take it in electrophysics, of course, you'll recognize that that looks just like a potential well in which you can have vibrational states. And that's exactly what we thought would happen. So you have like these vibrational states here, just schematically shown. But what are these vibrational states really? And there are states of two like in this case, rubidium atoms at a certain separation. And they vibrate like this. And that's like completely the same that you would also find for ground state molecules like H2. But here, the point is that the binding energy, like the binding separation of this molecule is 7 nanometers. So you have to have this basically a completely indifferent space, and the electronic clouds don't overlap at all, and still they form a molecule by all standards. Okay, and so here you see a measurement of these molecules. So the vibrational state 0 is here, and then 1 and 2, and you see they beautifully align. All the same, it's pretty harmonic, the spectrum. And you see like 50, 100 vibration states, and they all turn out in this measure. So the way this is measured is that you have a quantum gap microscope, so basically just like atoms on a square lattice, then you send it some light, resonant with these transitions, and you measure where atoms are lost as pairs, and then you interpret that as like the loss of a molecule, the Rydberg molecule. Okay, so now I want to shift your attention a bit like from this excitation process to some to what happens if you already have a molecule. Like let's say I have a molecule and it sits there on this lattice, and now I put on a strong laser field that can de-excite the molecule. And it does that by basically promoting one of the Rydberg atoms back to the ground state. And when that happens, of course, the molecule is gone. If I have a ground state and a Rydberg state, they don't bind anymore and the molecule falls apart. Okay, so we have this laser, and I will make that laser very strong. That's the story that I want to tell, but like, the conditions about which I want to tell. Talk to you about. So that's the molecule. That's the strong laser that couples this molecule and de-excites one of the Rydberg atoms. And when it de-excites one of the atoms, then basically the molecule falls apart. So there's a free continuum of motional states. So these are just, one atom flying this way, one atom flying this way. One is the Rydberg state, one is the ground state. It doesn't matter. Now it turns out this is a famous model, and in all physics is called the final model, a generalized final model. It doesn't matter. It's called the Anderson security model. But you basically have one bound state, you have a continuum of bound states, and then you have some coupling between them. That can be solved. So, and the interesting thing is that if now the energies here of this bound state are in the megahertz range, and the energies of this optical coupling are also in the megahertz range, then you can get coherent superpositions of this impurity with the continuum of states. And let me just comment that this is completely different from what you would see, for example, for water. So for water, you can have a similar physics. You can have water hydrate. You can put on a strong laser and you can try to rip off one of the hydrogen atoms. But that happens at completely different energy scales. So the hydrogen, like the vibrational frequency of the water molecules is in the tens of terahertz range, but the optical Rabi frequency is always the same. It can be in the megahertz regime. So we have a regime for water in which the vibration happens, and then once in a while, basically perturbatively, there's an ionization event happening. While here, you're in a regime where you can basically vibrate on one frequency and de-excite and re-excite on the same frequency. Okay, that's why we expect these eigenstates that are coherent mixtures between the bound molecule state and the continuum of motional states. Okay, so that's how you detect them, right? Like that's the fancy quantum gas microscope they have in Munich. Make a lattice of these atoms, you illuminate. It turns out that the diagonal distance on the lattice is just the right distance to make this molecule. Then you wait for a while. Then you take a picture. It can look like this, and now you computer reconstruct these loss signals as molecules. Okay, and so when you do that, you really have to think about like what happens more fundamentally to understand like how the spectroscopy of such a state would look like, or what it would look like. And so the trapped ground state of the optical potential are Gaussians. So you have a Gaussian motional state here, and you have a Gaussian motional state here. And so if I look at just two atoms, that's the entire picture. And here I try to plot the pair motional wave function of that atom in the coordinates of x1 and x2. So position of the first atom, position of the second atom. And because these are Gaussian states, like by the magic of Gaussian states, you can transform that to a center of mass and a relative coordinate, and it's still Gaussian. Okay, so that's this picture. And that's the trap picture. Like the trap, the wave function of the motional state of the trap atom. And now it turns out, like if you excite this molecule has the same center of mass wave function, so it's as spread as wide as the lattice function, but in the relative coordinate, the molecule is much more bound. So if you have no interactions between the atom and the acid and the lattice, basically they can have any separation within a certain range of like where the wide trap function of the lattice sits. But if you have a molecule, now they have a separation that's basically exactly 750 nanometers. Okay, so that's much more narrow here, and that will come in as an important ingredient. So now if you couple like this wide range of motional states to this narrow range of macrodiameter states, this molecule, then you might already imagine or anticipate that not all of the gray region will couple equally. The part of the gray region that has, the macrodiameter, the red region on top of it, will couple differently than parts of the gray region that don't have a macrodiameter. And that's exactly what we see. So that's that's a calculation that I did last year, I think. And you see that there are two lines, like a lower line, a higher line, and there's a central line. And now, because that's calculated, we can actually back out what the motional wave function of this molecule is. And it turns out that on either of those resonances, on the left and on the right, we see a nice narrow motional wave function. That's the part where the eigenstate of the system, the mixed eigenstate of the system, is coherent or adopts the molecular wave function. But then there's the central peak, and that's the part of the gray region that doesn't directly couple to the macrodiamond. And actually, the wave function of that looks like the wide Gaussian wave function that we had at the beginning, from which we have cut out and coupled away the narrow components. Okay, so these are new eigenstates that emerge, and we call them macrodiamonds. So they're kind of polaritons of the macrodiamond, these Rydberg molecules, and they're stable particles. I mean, like the lower macrodiamond is an actual quantum eigenstate, so it's completely stable. The positive macrodiamond is only quasi-stable, so you call it a scattering resonance. And it so turns out, I think I have enough time to talk about this, that the same physics that we just discussed, like this Fano model, like continuum model, so it's coupled Thomas state, is completely equivalent to Fano or to Feshbach resonance in scattering theory. So let's look at that. So we have the open channel, that's basically the motional space, and then we have the closed channels, that's the vibrational states here. And you can show that there's a scattering resonance emerging. So you always see, like, whenever there's a bound state, you see the scattering phase, like making a high phase jump. And now, as you increase the coupling strength, you see that there's the scattering, like this phase evolution is getting sharper and sharper here. So up to the point that when the two resonances are well separated, you really see a sharp jump of the scattering phase here. It's actually where this upper macrodiamond emerges. Of course, we cannot do a scattering calculation for an bound eigenstate, because that's just not resonant with any scattering, not the positive energy state. Okay, and so that's the theory, and now experimentally, what is measured? So here we see the atom loss basically as a function of the tuning for low coupling. So you see basically one resonance. Then as you tune up the coupling strength, so you make this, you push the system into the strong coupling limit. Now you see these two satellite peaks emerging. They become wider and wider. And we can summarize this in this fashion. So here I left out the central peak, 5 minutes. Great, yeah, I don't need more of that. So you see really like the two macrodiamond states split out and just separated by the Rabi frequency of the droplet. Okay, so that's like all about two particles. Now let's like think about a little bit further than that. So if we have a lattice of sites, so those are the black dots, and we can have a molecule on one pair, like sites 1 and 2, then we might as well have a molecule in sites 2 and 3, or 3 and 4, and so on. They can literally just appear on any one of those sites. And that's what I try to symbolize here. But through that process of de-excitation, now I can imagine a situation in which I have a molecule here, now I de-excite this atom, and I excite this atom, and the molecule effectively hopped from here to here. Right? I can imagine such a situation. And to verify this, I did the 3-particle calculation, so now 3 atoms in line. Do the same spectroscopic analysis, calculate all the eigenstates. So you see that now you have 2 coordinates, not just 1, relative coordinate between these two atoms, relative coordinate between these two atoms. And on these resonances here and here, you see that either one is quenched or the other one is quenched. And on the central one, you see the big blob of the two-dimensional Gaussian, now from which track the track into quench state states. And then what remains is the tiny peak here on the far left. That's the central peak. That's the peak where actually both the relative coordinate of atoms 1 and 2 and 2 and 3 are quenched at the same time. So the overall molecular wave function of that molecule is that of three atoms in a molecule state. And so that's kind of amazing because we started with an interaction that is binary, so that it's an electronic interaction basically between two atoms. And we end up with a new eigenstate that is three atoms. And we generalize that to more atoms, 3, 4, and 5. And unfortunately, experimentally, the measurements aren't good enough to detect this tiny point here. Spectroscopy isn't, but Simon did like some microscopy or quantum gas microscopy on these peaks to detect statistical correlations, and we actually see that it is like a two-body correlation, positive correlated signal, and a three-body correlated signal, so really confirming that these macro trimons, really like particles or molecules of three atoms do exist. Okay, so where do we want to go? We want to look at alignments that has to do with overlaps of these states. Look at interactions between macrodynamics, looking at higher lattice dimensions, and motion of macrodynamic lattices. Okay, so that brings me to the end of my talk. Let me just wrap up and leave you with some conclusions. So I wanted to show you that we have observed strong nonlinearities, and we can explain them in these semiconductor systems with Rydberg bouquet theory, shifting away from the old idea of ground state interaction. I've showed you that we have also observed Rydberg polaritons in the lab, collaborators have, but we haven't experimentally seen any quantum correlations between photons yet, and that's an outstanding challenge in project. Rydberg bouquet, I think, is an excellent mechanism to induce those photon correlations that we haven't seen yet, and we suggested some ways of making that happen even in lost environments. And finally, I talked about these Rydberg macrodynamics that can hybridize with the continuum of multiple states, and that process can be used, or that mechanism can be used to make molecules from binary interactions that consist of more than two atoms. Okay, thank you.
Thank you very much, Valentin, for this very interesting introduction of the overview of what is in training quantum phenomena. So, are there questions for you?
Yeah. First, just to clarify, so your three atom molecule, it's still just two Rydberg excitations. They're just sharing those between the three.
Yes.
Okay, just make sure. Okay, now a real question is in atomic Rydberg states, of course, angular momentum plays a huge role as well. So in your semiconductor Rydberg states, do you deal with angular momentum, or is that symmetry just pretty much broken by the lattice?
Oh no, it's not. So I mean, like this commitment to symmetry is not talking about the ground state excitons, where the lattice is somewhat comparable, or I mean, for most excitons, even then it's smaller than the size of the exciton. Now, as you go to higher Rydberg states, the wave function encompasses billions of crystal cells. Like it can be as large as a micron itself, like the Rydberg wave function. So that basically intuitively already tells us that the symmetry of the lattice doesn't matter all that much anymore, and it restores the free space angular quantum numbers. So in copper oxide, you actually denote the states with just atomic nomenclature, so you call them p states. And in the spectrum that I showed you, those were just the p states. Now, it turns out that that's a special feature of copper oxide, that it's the p states that are all different as opposed to the s states in the material that have the symmetries of the bands. And then it turns out that the breaking of the symmetry due to a crystal actually makes f states like just a tiny bit completely active. I don't know if I can bring up the slide quickly, and perhaps one doesn't even see it. Okay, well, that's wasn't the idea, but let me try. So you see that there's like like the F states actually get a tiny bit of optical dipole element, and you see them as tiny corrections to the spectrum. Right? Okay. Okay. Well, it's not very visible here. At all, that like here there's a like if you zoom into that region, there's like a tiny bit of that's the lattice structure expression that just makes F states. It's like
So what about the lifetime of these high isotonic Rydberg states. They live very close to the conjunction. Lots of stuff going on that you don't have to worry about in the atomic case. There's other excitations for lungs, and then there's also impurities that we can avoid. So I would expect them to have rather short lifetimes.
I mean, it actually turns out the lifetimes, I mean, they're short compared to how true, but actually the scaling of the lifetimes is atomic. So they, like kind of the lower states, or the higher states, lifetime is cubically enhanced from the ground state, actually longer. So they live much longer than the ground states. And this has been measured, but it turns out, and it's also reflected in the width of these peaks. So
the intrinsic, these peak widths reflect the
they, I mean, they're upper bound at least, or the inverse of that is an upper bound. So we see that the line width keeps shrinking up to around n equals 15. And then it somehow plateaus off. So there's some additional effect that kicks in and like stabilizes these life, or like doesn't let them like decrease further and further, as actually was predicted by Elliott in the 50s. And that has to do with, or like, why that is, people don't really know yet. There's a lot of, you know, as you said, like semiconductor effects. There's like whole theory about what people call the Irma scale. So basically effect states that someone leading into this all of these effects may matter. We don't really know. There might be free charges floating around, like from the exact conditions of the excitation. And we also see that, you know, these are the best crystals you can find. The natural crystals, if you make artificial crystals, they tend to be very worse. For some reason, people also don't really understand. And so then the Rydberg series somehow trails off, like around 15, 16. And all of this is due to the effects that you're mentioning. Okay. Thanks.
What do you mean by artificial crystal?
Say that again.
What do you mean by artificial crystal?
Oh yeah. Well, I guess the ones that you made. No, I mean this one is from a mine in Namibia. So something that people pick from the ground and call natural, and everything else artificial. Yeah, but I mean, it's very important, of course, to make artificial crystals, especially for these systems, because the mine that's, I think it's called the Sunak mine in Namibia, is now closed. So there are certain people that, what's that?
You mean the lab grown, not the sterile.
This all these great crystals from Namibia. Mine is closed. Some people have bags of this material, some are lying in their labs. Like groups in Cardiff and some else are trying hard to make artificial crystals, but they're in Stockholm, they're running into, you know, certain difficulties, right? Like, yeah, I mean that's what people speculate. But somehow, like the natural crystal, like just by plain eye inspection, looks more messy than the artificially grown crystals, and still it has a better efficiency. It's not making it strain, making it the exact growth conditions. It's not completely clear how to make like, the perfect crystals. But that said, I think even with artificial crystals that like trail off at 50, you can do lots of interesting things that people do. Like you don't have to have this perfect crystal that goes up to 30.
I actually the first one would be, I mean, if one suspects that there could be defects in this structure, when one has lab on crystal, shouldn't one run it by or allow program to see where the reflected peaks are stronger? I mean, if there is a or just, you know, mathematically do away with the atoms in the crystal layer by layer and look at them in an electron microscope and see if there really are, you know, defects in the or dislocations in the crystal structure. One should have a good measure of the
size of the quantum orbits of the excitons, so if one this should narrow down the distance range where one would otherwise be looking for.
Yeah, I mean, okay, so first disclaimer, I'm not the expert on exactly like this, but I know that, seeing that the exciton radius is so large, the spot size does matter a lot. So even on the same crystal, people are trying to find the spot size. On south spots, they see exciton numbers up to like 20, and others only to 15, and then they pick the spot where they can go to higher principal quantum numbers. Like sometimes the line width doesn't scale exactly as expected. And so Thomas Bollier from Toulouse is developing like a numerical technique where he scans the crystal and then picks, like somehow automatically picks the spot, but that's based on the Rydberg series. So he doesn't really look for defects, and I'm not sure if you can. I think the leading hypothesized problems are oxygen vacancy centers, and I don't know if you could just see them somehow experimentally.
Interesting. The second question, could you bring up towards the beginning of your talk? There was this spaghetti figure of states.
Yes.
And you use the word spaghetti.
Yeah.
And this is the one. Are these avoided crossings or are these true crossings of pairs?
These are all avoided crossings because I use all the symmetries in the system. So I log diagonalize the system first by symmetry, and then diagonalize every symmetry separately. So all crossings here are avoided.
Are avoided. You just don't see it on the scale.
Yes. Yeah.
It's one of them.
Yeah, I mean, the coupling generically can be very small, right? Like just by perturbation theory, then like if it's finite, and there's two cross, then there's tiny cross, like a tiny cross.
Okay. And if you were to zoom in on them, you can see that.
Yes.
Then the last question: these macro dimers, I mean, they are huge entities.
Yeah.
What are exactly the demands on the experimental apparatus? Because I figure, if you have such a large construction floating around anywhere in your apparatus, where, your quantum objects, your Rydberg states are large already, and then you form an even larger object from two large objects.
It's as large as bacteria, basically. Yeah.
Yeah. So, do you have to do this in an ultra-high vacuum, or why are these states not destroyed by interactions? I mean, one could think, anything that flies around there will destroy these macrodynamics. What else?
So, I mean, like naturally, the lifetime of this molecule is about as long as a Rydberg state itself. Because as long as there's a Rydberg state, there's this binding mechanism. And of course, we know that the Rydberg state doesn't live forever. In fact, its lifetime is somewhat a little bit of a microsecond range of polaritons numbers. And experimentally, it's somewhat shorter. And that's been, like a conundrum of Rydberg, or like the nemesis of Rydberg physics, I guess, even in atomic systems, that there are other decay channels like black body radiation. If you haven't made your vacuum cold, then there are like microwave photons flying around and bumping into those systems and making state transitions. And as soon as that happens, which is like a fundamental problem, like, for example, Rydberg pressing, then as soon as that happens, you lose the microdynamic. But we can measure the lifetime of these states, and they're long enough. I mean, like they're easily long enough to measure them, and like maybe like if you want to build a quantum computer out of them, then you might run into coherence issues. But like in principle, the lifetime is roughly given by the lifetime of the very state.
Yeah. And what's the environment which these experiments are carried out? Is it ultra vacuum? Is it?
I mean, it's a quantum gas microscope of the standard type that's also used, for optical lattice experiments. It's of course a vacuum. Yeah, I can't give you a number of how good the vacuum is, but I mean, it's a vacuum chamber.
It doesn't need to be that good. This is what I used to do for just Rydberg states, not all of those. We could go up to 100, which is way bigger than this, and you just very seldom ever see losses. Yeah, and that, I didn't have anywhere close to, it was just a confusion. It's really not a problem.
Is that because the excitation cross section is small, or because you can dilute everything so well that the,
Yeah, it's just the collision times are fairly small.
okay?
Yeah. Or collision, sorry, rates are others. You're just not a problem.
Okay, interesting.
I do have a problem along those lines, so, there's a problem, and I've kind of forgotten the name, I think it's super radiance.
Oh, yeah.
But it's when you have, closely packed river states, and you try to make them bigger and bigger, they start interacting, and they go super radiant, and they just go like, if you're in 20, you go 19, 18, 17, and emit light. Do you have to worry about that in these systems?
I mean, so super radiance, I mean, happens when they're very close, right? Like then, like kind of the sticky super radiance happens when they all couple of the same mode of the vacuum field. So I would say in principle not, but actually there are some experiments, like rare events in this oil and gas microscope, where it somehow happens that, instead of losing gas atom, suddenly, like once in a while, you lose an entire diagonal. So that's actually a funny picture. You see this entire thing like up and there's a diagonal gone. It's not completely microscopically understood why that is, but it could be one of those we call it avalanche processes. And sometimes the entire one is gone. It's very, very, very rare, but like that happens. And yeah, the origins of that are not known. I mean, we've like thought about collective effects, like not only super radiance, but exchange attractions, black body radiation, collective shifts, all of this stuff. Maybe it could be that there's like an atom like really gets kicked out at the when the molecule breaks apart and it kind of ballistically kicks out atoms. So we don't know. But they kind of these chain reactions and that processes are all the candidates that could be out of that.
Okay, so due to the interest of time, we should stop now, and please feel free to read Valentin after the termination of the discussion and discussion here. So, thank you.
So I looked